All right, so this is the next installment here of Infinite Series, and we want to look at some examples. I did want to point out that I missed the last part of the definition of an infinite series. Yes, an infinite series is a sum of an infinite number of terms of a sequence, and the partial sums are indicated by S sub k. And if there is a limit as k goes to infinity of the partial sums, we say the series converges. But of course, if there is not a limit, we say it diverges. All right, so if the limit of the partial sums does not exist, then we say it is a divergent series. If the limit of the partial sums does exist, then we say the series converges. All right, a word about index notation. Before I had mentioned in 5.1 that sequences could start at n equals any particular value. It doesn't have to be n equals 1. The same thing with series. You don't have to start always at n equals 1. You could relabel the indices. So notice here that the one that we were looking at in the previous example, we get this for the series. So here, infinite series is going to be the sum from n equals 1 to infinity of 1/2 to the n minus 1. And notice when n equals 1, this exponent is 0. When n equals 2, this exponent is 1. So the exponent on 1/2 starts at 0. So if you wanted to, you could relabel this at n equals 0 and then change this power to be just n. So here, this representation, starting from 0 to infinity, where the terms are 1/2 to the n, is equivalent to what I have here. Now notice, there's nothing special about starting it at 0 either. Heck, I could start at 5. So if I start at 5, I want this exponent to be 0. Just like when I start at 1, I want the exponent to be 0. When I start at 0, I want the exponent to be 0. So here, notice that if I start at an index of n equals 5, then this power has to be n minus 5, or else it won't be the same series. Okay? So the reason we would change the way the indexes appear is because we want to do algebra with these series. And when we do algebra with series, we really want the indices to match up. Later on, if you take differential equations or other courses where you deal with solving complex integral equations or differential equations, oftentimes it can be written in terms of series notation or series solutions, and you want these indices to match. Okay, so here's another example, but we're going to be a little bit more explicit about how we did this. So here I've got the series from n equals 2 to infinity, and here the terms in the series are 1 over n squared. And let's say that I wanted to start at 1 instead of 2. So I'm going to relabel a different index. I'll call m. And it's going to be, if I want to start at 1, then I'm going to have n minus 1, right? Because n starts at 2. So when it first starts, 2 minus 1 will be 1, and then I can start at 1. Okay. Now, if that's the case, if I'm going to start with m that starts at 1, and I'm going to define m as n minus 1, that's how I got the 1, then solving for n is going to be m plus 1. So now wherever I saw an n, I'd have to replace it with m plus 1. And now I completely converted this series that started at 2 to a series that starts at 1. At this point, you can switch back to n equals 1 to infinity 1 over n plus 1 squared if you want to keep the letter n. This just gives us an intermediate safety catch so you convert these indices correctly. All right, let's look at an example of 3 different series and to see if these series converge or diverge. All right, for the first one, we have the series from 1 to infinity of the terms n over n plus 1. So we'll look at that. So let's look at the partial sums. Remember, when we're trying to find if a series converges, we look at the partial sums. So the sum of the first term is, well, 1/2. Remember, this is going to be n over n plus 1. So these things are going to be looking like, for the first one, 1 over 1 plus 1, which is 1/2. Then I'm going to have 1/2 plus 2 over 2 plus 1, which is 2/3. So that's what the sum is for the first two. S sub 3 will be 1/2 plus 2/3 plus 3/4. Notice I'm adding the first three terms. S sub 4 would be adding the first four terms. Okay. Now if I look at this, now I'm going to try to find some type of pattern. It's not exactly clear here. So here I got S sub 1 is 1/2. S sub 2 is 1/2 plus 2/3. But this 2/3 is definitely bigger than 1/2. So here 1/2 plus 2/3 is bigger than 1/2 plus 1/2. I just replaced the 2/3 with 1/2. So therefore this is bigger than 1/2 plus 1/2. That's 2 times 1/2. For the third partial sum, I've got 1/2 plus 2/3 plus 3/4. And the same thing. This 2/3 is bigger than 1/2. This 3/4 is bigger than 1/2. So S sub 3 is going to be bigger than 1/2 plus 1/2 plus 1/2, or 3 times 1/2. Similarly, S sub 4 is 1/2 plus 2/3 plus 3/4 plus 4/5. And each of these terms in the sum are bigger than 1/2 from the second to the fourth. So that's going to be bigger than 1/2 plus 1/2 plus 1/2 plus 1/2, or 4 times 1/2. In any case, we can see that the partial sum, let's say S sub k, for arbitrary k, is going to be bigger than k times 1/2. Right? S sub 2 is bigger than 2 times 1/2. S sub 3 is bigger than 3 times 1/2. S sub 4 is bigger than 4 times 1/2. And we come to the general conclusion that S sub k is bigger than k times 1/2. Right? For every integer k. Therefore, this sequence of partial sums is unbounded. Right? Because S sub 2, S sub 3, this is an increasing sequence. And so therefore, if it's increasing, it's going to be, and it's unbounded. Okay. So therefore, we can conclude that since the limit of these unbounded partial sums would be infinity, right? So if I took the limit of S sub k, it's bigger than k times 1/2. So the limit of S sub k as k goes to infinity is bigger than, well, arbitrarily large k times 1/2. This thing is divergent. So therefore, the series of the terms n over n plus 1 diverges. Okay? So these things are often not easy to see because I have to do some type of bounding argument. Here, the strategy was, well, let's see if these partial sums are not bounded. Can I come up with a formula? And we did. The partial sums are bigger than k times 1/2. Well, if that's the case, then the limit as k goes to infinity is going to be, essentially infinity times 1/2, which is infinity, which would imply that this series diverges. Let's look at part B. I have minus 1 to the n. I'm going to add all of those terms. Notice that for n equals 1, it's going to be minus 1. N equals 2, it's going to be 1. N equals 3, it's going to be minus 1. So I'm going to be adding minus 1 plus 1, minus 1 plus 1 forever and ever. Let's look at the partial sums. If I add just the first term, it's minus 1. If I add the first two terms, it's 0. If I add the first three terms, it's minus 1. If I add the first four terms, it's 0. And so this is going to go back and forth between minus 1, 0, minus 1, 0. And so the limit, right, here's the S sub k, it's going back and forth. The limit of the, as k goes to infinity, of S sub k is divergent. It's not because it goes to infinity, it's because it doesn't converge to a real number. So because the limit of the partial sums does not converge, this series is divergent. Right? So the sequence diverges. Lastly, let's look at the third series. I've got the series of 1 over n times n plus 1. So the terms that we're adding repeatedly all have the form 1 over n times n plus 1. So let's go ahead and dig into the partial sums. All right. The first sum is just going to be the first term. 1 over n, which is 1, times n plus 1 would be 2. So it's 1/2. S sub 2 is the first two terms added. So There's the first term. There's the second term, right? The second term would be 1 over 2 times 2 plus 1. That's the 3. And we get 2/3. If we add the first 3, there's 1, 2, 3, and do the algebra, we're going to get 3/4. If we add the first 4, we're going to get 4/5. If we add the first 5, we get 5/6. So a lot of this, it's really important that you have your algebra skills honed, because if we don't get these correctly simplified, we may not see a pattern in these partial sums. So in general, S sub k, based on our pattern here, is going to be k over k plus 1. Notice for 2, there's the k over k plus 1. For S sub 4, there's the 4 over 4 plus 1. For S sub 5, there's the 5 over 5 plus 1. So the partial sums, S sub k, can be defined in general as k over k plus 1. So the limit of the partial sums as k goes to infinity, right, would be the limit as k goes to infinity of k over k plus 1. And if we use L'Hopital's rule, right, because we have infinity over infinity, using L'Hopital's rule and differentiating, we'd get 1 over 1, and that's 1, so the limit as k goes to infinity of 1 is 1. So the limit of S sub k as k goes to infinity is 1. Therefore, the series converges, and it converges to the value of 1. All right, so something to notice in these first 3 examples. It's very, very important to look explicitly at the partial sums, S sub 1, S sub 2, S sub 3, right? We did that for all of these. We looked at specifically the partial sums. And then from there, either try to bound these partial sums, find a pattern in these partial sums, and if you need to, find a limit of these partial sums. Okay? So once you get a general formula for the partial sums, you can apply a limit. This one was 1. Over here, this doesn't have a limit because it goes back and forth between -1 and 0, but I got a general idea of what S sub k is. For the first one, here S sub k was bigger than k times 1/2. I got a general inequality in this case for those partial sums, and this is easy to see that as the limit as k goes to infinity, this blows up to infinity, and so it's divergent. All right, let's look at some more examples in the next video.